Okay, so we are still discussing improper integration. So what we want to do, what we are doing at the moment is we want to extend the notation of the definite integral to include cases where the upper or lower limits are either plus minus infinity, and then also other cases where the integrand is not necessarily continuous at some point. Now, we already discussed the first type where one of the limits is infinity plus minus infinity. This is called type 1, infinite integrals. And just to remind you, so the definition is the definition of this symbol is, okay, you have a function f which is assumed to be continuous on the half open interval from a to infinity. So you can compute all of those integrals if you go from a to t. And now you check whether the limit as t tends to infinity exists or not. If this limit exists, then we call this integral convergent. And the value of this integral is defined as this limit. And if this limit does not exist, we call this integral divergent. So, and we have the same definition if we integrate from minus infinity to a, and we have a similar definition if we look at this integral. So if we have a function f of x continuous everywhere, and we look at this integral, then we define it. So we choose any point a, you can freely choose it, and we look at those two infinite integrals. And if both of them exist, we say that this exists as well, and and the value of this is the sum of those values. And this does not depend on the point a. So the a you can freely choose. If one of those integrals does not exist, okay, then this integral does not exist as well. So then we say this integral is divergent. Okay, so last time we started to discuss already a couple of examples. We saw that if you look at this function 1 over x squared, then we saw that this integral is convergent. The value is equal to 1, so convergent. Okay, and we saw that the integral dx over x, so if we replace the power here by 1, then this integral becomes infinity, divergent. Okay, so more general, we saw that if we look at functions dx over x to the b, then in case of, so if p is larger than 1, then convergent, and the value is 1 over p minus 1. And if p is smaller or equal than 1, divergent. Or you can say it's infinity. Okay. Now, so this roughly tells us, okay, if we look at such functions 1 over x to the p, because you can interpret this as an area. Okay, so you have this function here. Okay, so this is our function y is equal to 1 over x to the p. Okay, and so actually the motivation behind defining this symbol is to define this area here, so the area below the function and above the x-axis, or to extend our area definition to include such areas which where we here consider infinity. Now, this roughly tells you, okay, that if p is larger than 1, okay, then, or this tells you that if p is larger than 1, the area exists. Otherwise, the area does not exist. So it's the existence, whether such a integral is convergent or not, okay, depends, roughly speaking, on the speed at which the function, as x tends to infinity, tends to 0. Okay, if the function tends to 0 very quickly as x tends to infinity, okay, this symbol here is the improper integral is likely to exist. Okay, if this speed of convergence is not fast enough, okay, then the speed of convergence to 0 is not fast enough. Okay, this symbol is not going to exist. And of course, if you consider a function, okay, which does not tend to 0 as x tends to infinity, okay, this symbol clearly will not exist for such functions. Okay, so this is also helpful because this kind of for other functions you can already looking at the behavior at the speed of convergence to 0 of the function. Okay, you can already, and comparing it with this function here, you can already determine just by looking at the integral whether the integral will exist or not. So it's kind of existence of convergence to test whether the integral is convergence and to find its value. Two different problems. And the problem of determining whether such an integral is convergent or not, normally more easy. Okay, we will see this. I will make this more precise in a few minutes by introducing a test which helps you to find out convergence, but not necessarily gives you the value if the integral is convergent. But just to emphasize what I mean, okay, if you look, for instance, at this function here, let's say e to the minus x dx. Okay, without even computing the integral, okay, we will say this integral will be convergent. The reason being that we know that e to the minus x, okay, as x tends to infinity, goes to 0 very, very quickly. And in particular, this very, very quickly, if I say very, very quickly, what do I mean? Much more quicker than any of those functions, 1 over x to the p. Okay, so for x large enough, e to the minus x will be certainly be smaller than 1 over x to the, for instance, square. Okay, and so this roughly tells you this integral should exist without doing any computation. Okay, you should for this I will make this precise in a minute how to do such tests for convergence. Okay, but you should roughly understand that if you understand those functions and more classes of functions, similar classes of functions, it's quite easy to determine whether such an integral is convergent or not. But in this case, of course, also easy to compute. If we go to the definition, then we have to look at the limit as t tends to infinity, the integral from 0 to t e to the minus x dx. Now, because in this case, this integral is easy to compute, but this is not necessarily not necessarily true for all functions. So we have here minus e to the minus x evaluated at 0 and t, and we see, okay, this is the limit as t tends to infinity, 1 minus e to the minus t, and indeed, if t tends to infinity, this tends to 0, so we have 1. Okay. Now, maybe you have heard in other classes that an important tool in applications, so-called Laplace transform. So normally, if you have given a function, this is something which is important in electronics and so on. If you have a function, then we define a new function which depends on the s. Okay, so you choose an s, and then you define a new function like this here. So you have given a function, you define a new function, capital F of s. This function is called the Laplace transform of the function small f. I guess you have heard this maybe in applications. I do not want to do any computation, so it's quite easy. For instance, if you choose f of x equal to 1, you can quite easily come up with the Laplace transform of the function f is equal to 1. But what I want to stress is, okay, why are engineers interested in this kind of function? I'm not going to explain why they are interested in this function, but I should explain why do they choose this function here. Okay, because actually you can replace this by other functions, and there are indeed other transforms like Fourier. This is Laplace transform, like Fourier transform and so on, which use here another function. So there are quite a lot of other so-called integral transformations. But this is quite a natural choice, because this tells you that, okay, because you actually want to have that for many s, this integral here is convergent. Okay. Now, if you look at, if you want to understand whether this integral is convergent or not, you have to look at the speed at which this function for a fixed x s approaches 0 as x tends to infinity. Okay. But we know that this function tends to 0 very, very quickly. So unless f of x does not behave too badly, okay, if f of x, of course, grows very fast as x tends to infinity, this will not exist, okay? But even for f of x which do not tend to 0, okay, normally this function here will beat this function, okay, and the growth to 0 will still be fast enough such that this here exists for many, many s. That's the reason why this function is chosen. Okay, it's kind of arbitrary. Maybe you have seen this in applications. And of course, now using this kind of notation, you can, for several functions f, you can easily come up with the Laplace transform of this function. I'm not going into details. I just want to, my main purpose of introducing this is just to explain why the choice of this function here. You should roughly understand this. Okay. Now, so we saw already that, let's go back to this class of improper integrals. So we saw that if p is larger than 1, then this is convergent, and the value is 1 over p minus 1, and infinity if p is smaller or equal than 1. From this, it's quite easy to find similar integrals. For instance, if you look at this integral from e to infinity, and then you have a dx over x times ln x to the b. Okay, it's kind of, you see that the boundary here, the boundary case is the case p is equal to 1, okay? This is the function, 1 over x is the function which separates the good from the evil, okay? Because here you see that if p is larger than 1, these are the good functions. p is smaller than 1 is the evil ones, and 1 over x is the boundary point, the boundary function. Now, so of course you will be interested, okay, if you look at 1 over x, but you multiply it with something, okay, you make it a little bit smaller or larger, okay, for which cases of p does this integral converge? Okay, but this actually the behavior for this one is the same as this one, because you use the transformation u is equal to ln of x, which means then that du is equal to dx over x. Okay, and then this integral here transforms into the integral, so the lower limit becomes 1, the upper limit remains infinity, and then you have here du over u to the b. And the behavior of this one is determined by this one. Okay, so you see this will be equal to, if I'm just interested in convergence and divergence, so this will be convergent if p is larger than 1, and divergent if p is smaller or equal than 1. Also, this is helpful sometimes. Similar, you could consider dx over x ln of x to the p, and you can choose similar transformation. Actually, you can write dx over x ln x ln x ln x, and so on, and then till you have n ln's and to the b, and you will always have the same behavior. Now, another interesting example, maybe to emphasize, is this one, the integral from minus infinity to infinity x e to the minus x squared dx. Okay, if we have something like this here, we have, by definition, we have to split it into 2. And we have to discuss those two guys separately. Okay, so for the first one, so the integral from 0 to infinity, x e to the minus x squared dx. Now, by definition, this is the limit as t tends to infinity. Now, of the integral from 0 to t, but since we have here an x, this is fortunately easy to compute over the minus. Okay, so you see that, sorry, I shouldn't write it like this. I should write here till t. So this is the limit as t tends to infinity. And then we have here e to the, so 1/2 minus e to the minus t square half. And again, this is convergent, so this is equal to 1/2. So this is convergent here. Actually, you see that sometimes we drop here the limit and just evaluate the integral like this and write here from 0 to infinity, meaning that at the upper limit we have to at the upper limit here we have to take the limit actually. Now, if you do the same for this integral here, x e to the minus x square dx, actually you can make the substitution u is equal to minus x. X is equal to minus u. Okay, then this here transforms into the integral from infinity to 0. Now, so this one here becomes minus u e to the minus u square, and dx is equal to minus du, so we can drop this. So actually, this becomes the integral from 0 to infinity minus u e to the minus u square. Okay, this is just minus this integral here. So the same reasoning gives you that this integral is convergent equal to minus 1/2. Okay, so overall, because this integral is convergent as well. So this integral will be convergent. The value will be equal to 0. Okay, I should stress, if you see such an integral, okay, of course you could say, you look at the integrand, the integrand is an odd function, okay, so the integral should be equal to 0. This is not always correct, okay. This kind of reasoning is not always correct. What is the problem for this kind of reasoning? You say this is an odd function, okay. So it's kind of if you plot this function, okay, then you have some part. If you're going to plot this function will look like something like this here. Okay, so if you look at the area equal to 0. Okay, but this kind of reasoning is not correct. Okay. Who understands why? Yeah, right. You have to check first whether the integral is convergent. This is important. Okay. So, because you can, for instance, the same reasoning would be true if you drop this one here. Okay. Then you can also say this function here symmetric. Okay. So the integral should be equal to 0, but it's not true because those two integrals will not exist in this case. So this integral does not exist. Okay. This is the first important remark here. The second important remark is, okay, if you would define this symbol, okay, if you would define this symbol as the integral from minus t to t x e to the minus x squared dx, okay, the definition would be different. Because if you define the symbol as, this symbol is not defined like this here, okay, I should stress this, okay. This symbol, because this symbol is defined as the limit t tends to infinity, integral from minus t to 0, x e to the minus x squared plus the limit s tends to infinity, integral. They are not necessarily the same here. Okay? And you cannot merge them, okay? Because you do not know whether they exist, okay? So this is quite important, okay? Because I know that students get quite often confused by this. This here, like in engineering, electronics, okay? Sometimes this symbol is defined like this here, okay? It's called the mean value. And then I guess, if I remember correctly, they add here an h. So this is another definition of this symbol. The definition would be like this here, okay? Because if you define this symbol like this, then indeed, of course, this one is 0 because this function is symmetric here and will be equal to 0. But if you would use this definition, then you can say that this would be 0 as well. So using another definition. Okay. Sometimes you see this. Okay, for engineers, sometimes it's equal to 0. Okay, because they use this kind of definition. If the integral is convergent, this is true. Okay, but the inverse, not necessarily. Okay, if this limit exists, this integral is not necessarily convergent, as this example shows. Okay, it's important to stress. The problem here is how you define it. Okay, if you would define this symbol here, like this here, okay, then you could compute for much more functions f. This symbol here would be convergent. This is the main message. Any questions to this? So whenever you, I should say, if you have already checked that this symbol is convergent, okay, then indeed you can compute it like this. Okay, but if you compute this integral like this, you have to check first whether this integral is convergent or not. Okay, any questions? If not, then we move on to type 2. Now, a type 2 integral is, so now in difference to this situation, we allow that the function is also discontinuous at one of the boundary points. Okay, so you have a function which is continuous on the half open interval AB, okay, and discontinuous, not continuous at B, okay, not continuous on B, okay, but still you can consider this integral here, the integral from a to t f of x dx. So if t is smaller than b, okay, no problem, okay, then you can consider this because the function is continuous. So what we do is we look at the limit as t tends to b from the left, okay, and if this limit here exists, okay, we will say that this integral here exists, okay. If this limit does not exist, this integral will be called divergent, okay. If the integral exists, convergent, then we will define the value by this limit here. Okay, this is so-called type 2 improper integral. Okay. Okay, so any questions to this? No? For instance, let's maybe look at an example. For instance, let's look at dx over square root of x to the cube. X is enough. Okay, so for instance, let's look at this integral. Okay, so we first of all we see that. So actually, this is for the right boundary, but we have the same definition for the left boundary. Okay. So if we look at this integral, okay, the integrand at the left boundary is equal to 0. Okay, so this function is not continuous at this point here. Okay, so this is really an improper integral of second type. Now, what we have to do is, okay, we have to look at the limit as t tends to 0. Now from the right, it's different from here where we have the left boundary. And we'll have to look at the integral from t to 3 and then dx over x to the 3/2. Now, but this is of course easy to compute. So we have the limit t tends to 0 from the right, and now for this we have over minus 1/2 evaluated at t and 3. So you see that. Okay, so we have 2 times, and then we have t to the 1 minus half minus 3. But you see that as t tends to 0, this will tend to infinity. So this is infinity. So this integral is divergent. Okay. So in other words, if we look at draw the function. Okay, so if we draw this function here, this function will look like this here. And you have here 1, 2, 3. Then this means that this area here, okay, won't exist, okay? Or you can say, okay, the area exists is equal to infinity, okay? Because actually the reason for defining this symbol, again, because we want to extend our area definition, okay? You see also that if you look at this exponent is larger than 1, okay? If you do not consider the integral from 0 to 3, but from 1 to infinity, okay, from 3 to infinity, the integral will exist, okay? So it seems that what we should study is the integral from 0 to 1 dx over x to the p, okay, for general p, and check out what is the difference to the type 1 situation. Okay, so let's replace this by the general one. Okay, so let's replace this by the integral from 0 to 1 dx over x to the p. And let's find out for which p does this integral exist. Now, we saw already that if p is equal to 3/2, this integral is not going to exist. Now, if we look at the general situation, we consider again the limit as t tends to 0 from the right. And then we have the integral from t to 1 dx over x to the p. So this will be the limit as t tends to 0 from the right. Okay, here we have x to the minus p plus 1 over minus p plus 1 evaluated at t and 1. So this will be the limit t tends to 0 from the right. So at the upper limit we have 1 over minus p plus 1 minus, and at the lower limit we have t to the minus p plus 1 over minus p plus 1. Okay. Now, because we consider this limit, so we have to assume that minus p plus 1 is larger than 0. Okay, so for this case, you have to check out that there is one case where minus p plus 1 is equal to 0, but this case is p is equal to 1. But in this case, the integral is not like this. Okay, it's different. Okay, so we actually here I excluded the case p is equal to 1. Okay, otherwise this is not the antiderivative of this function. Okay, so if we have minus p plus 1 is larger than 0, then you see that this term here tends to 0. Okay, so in this case, the integral exists and is equal to 1 over 1 minus p. And if this is smaller than 0, okay, this integral will not exist, will tend to infinity. Okay, so we see that the behavior of this integral, okay, is kind of, I should say we also have to check the case p is equal to 1, but this case is also is simple. Okay, let's check the case p is equal to 1. So in this case, we have the limit p tends to 0 from the right, and then we have ln of x evaluated at t and 1. So what we get is the limit t tends to 0 from the right minus ln of t, which is infinity. Okay, also divergent. Okay, so we see that this kind of integrals, so the integral from 0 to 1 dx over x to the p, okay, are convergent and equal to 1 over 1 minus p if p is smaller than 1, and infinity if p larger or equal than 1. So that the kind of the behavior, if you compare this with the case from 1 to infinity, is reversed. Okay. Of course, this is kind of expected because, for instance, if p is negative, okay, this integral will certainly exist. Okay. So for p is smaller or equal than 0, this integral certainly exists because it's not improper. Also, this again tells you something about the speed of because what you again need is as you see that if x tends to 0, this will go to infinity. Okay, but if p is larger than 1, okay, if the speed with which the function approaches infinity is fast enough, okay, then the integral will exist. Okay, otherwise it will be divergent. Okay, so for instance, if you look at the integral from 0 to 1 ln x dx, Okay. So again, you have to look at the speed, okay, with which this function approaches plus or minus infinity. Okay. So here the speed with which this function approach. We know that if you if you plot this function y is equal to ln of x, okay, then as x tends to infinity, okay, this function goes to infinity very, very slowly, okay. But as x tends to 0, this function goes to minus infinity very, very quickly, okay. Since the function is going to minus infinity very, very quickly, okay, this area should exist, okay. You also have to compare this with this here, okay. So here you look at the speed with which the function tends to infinity. If the speed is large enough, okay, then the integral will exist, otherwise not. So for this integral, we certainly expect that the integral exists. We can check this. So by looking at the definition, again, the limit as t tends to 0 from the right. And we have to integrate this function here, which is x ln of x minus x, evaluated at t and 1. Okay, so which is equal to the limit t tends to 0 from the right. So you see for the upper limit, we have minus 1. And for the lower limit, we have minus t ln t plus t. Now this is equal to 0, and this will tend to 0 as well, because the speed here is fast enough. So what we get is minus 1. Here, of course, for this vector, for this part, you have to use the L'Hopital in order to check it. Okay, so any questions to this? Now, until now we have just considered the cases where the discontinuity is either the left or right boundary. Actually, all examples we saw is left boundary. Okay, but sometimes it can also happen that the discontinuity is inside the integral. Okay, so you have a function f which is discontinuous at some x is equal to c and continuous for all x in some interval, let's say a b, without the c. Okay, so in this case, this symbol, if you look at this integral, so now f of x is you have some point inside the integration interval where f of x is not continuous. So the definition of this symbol is now again as for the type 1. Okay, you have to look at a c, and then you have to look at cb. You have to look at those two separately. Okay, and then you have to figure out whether both of them are convergent. If both of them are convergent, this one will be convergent as well. If one of them is not convergent, this one will be divergent. Okay, so this is the definition for the type 2 improper integral if the discontinuity is inside the integration interval. Okay, and here you have to be careful, okay, because sometimes it's easy to overlook that there is a discontinuity inside the integration interval, okay. So sometimes if you have given an integral, you find an example in our textbook. For instance, this example here. Okay, if you are not careful enough, okay, because actually you see, this is an improper integral. It's not a proper integral, okay? Because x is equal to 1, okay? This function has a discontinuity, okay? If you do not check this, okay? If you would immediately apply the fundamental theorem of calculus, okay? You would say, okay, this is the ln of absolute value of x minus 1 at 0 and 3, okay? So you see this is the ln of 2 minus ln of 1, which is 0, ln of 2, okay? of course, this answer is wrong, okay? So if you do not check carefully whether the given integral is improper or not, okay, you could run into problems. Okay, so I should emphasize that this is wrong here. This is something which frequently occurs in the Heu-Kau. Given an integral, okay, the question would be, okay, the value of this integral is equal to, then for instance you have ln of 2 as one choice, you have 0 as one choice, as another choice, 1 as another choice, and the third one is none of these. Then you have to say none of these. Okay, because the reason is actually you have to look at this. You have to break it into two parts. This is the first part plus this is the second part. And then you have to check separately whether those two are convergent. Okay, but for instance, okay, if you now apply the limit, okay, so the limit t tends to 0 from the right of ln absolute value of x minus 1 evaluated at t and 1. So you see that this is the limit as t tends to 0 from the right. Now for the upper, this is the wrong one. Sorry. Because the problem is the upper limit. Okay, so you have, sorry, you have this one. Now you see that this is the limit. T tends to 1 from the right. So you plug in t here. The absolute value is ln of 1 minus t minus, at the lower limit you have 0. And now you see, okay, if t, because this approach is 0, okay, so what you get is minus infinity. Okay, so you see that that this integral is divergent. Okay, hence this integral is divergent as well. Okay, so this integral is divergent. The other integral would be divergent as well. Both are divergent. Okay, so you have to be careful here. This is something which this is a kind of exercise which frequently shows up in the Heu-Kau. Okay, you have given something like this here, and it just checks whether students are able to check whether this integral is proper or improper. So first, you always have to check whether the integral is given the integral. You always have to, before you do the computation, okay, check whether the integral is improper integral. Of course, type 1 is easy to recognize because one of the limits is infinity, plus minus infinity. But type 2, okay, is easy to overlook. Okay, so any questions to this? Okay, so as I have already explained, okay, normally if you have given an improper integral, okay, you have to do two things. The first thing, you have to check whether the integral is convergent or not, and in case the integral is convergent, the second step would be to find the value, okay. Now, I told you already these two steps are, the complexity, the difficulty of those two steps, okay, are not the same. Normally, it's much easier to find out whether a given improper integral is divergent or not than computing the value. Computing the value can be quite complicated, okay. And in order to find out whether a given integral is convergent or not, okay, there are kind of tests. One test which is introduced in our textbook is the so-called comparison test. So the main aim is now to check whether a given improper integral is convergent or not. So for this you can use the comparison test. You assume you have given two functions which satisfy this relation here and are continuous. On it doesn't matter, let's say this interval here, or let's say a to infinity. Okay, so let's assume you have given two continuous functions which satisfy this relation. Now, the first part is if you can prove if the integral from a to infinity f of x dx is convergent, then the integral from a to infinity of g of x is convergent. And secondly, if the integral from a to infinity g of x, d of x is divergent, then the integral from a to infinity of f of x is divergent. Okay, so this is something which is pretty obvious if you look at the area definition. Okay, or if you interpret all the given integrals as areas. Because you have two functions now. G of x, and you have another function f of x, which always remains above the function g of x. Okay, now the first part tells you if the area below f and above the x-axis exists, the area below g and above the x-axis will exist as well. And the second part tells you if the area below g and above the x-axis does not exist, which means the area is infinity, then the area of below f of x and above the x-axis will not exist as well, so it will be infinity as well. Okay, but actually, I should maybe stress this is not so easy to prove for us. Okay, it's easy if you know a little bit more. Okay, but we are lacking one tool here to prove this. Okay, maybe it's worth it to look at how far we can go if we want to prove it. Okay, just to see that because this is something which I guess everyone will say this is obvious. Okay, just to see that. Also, this is completely obvious. We are not able to prove it because we are lacking only one tool. So you see, so for instance, for the first part, what you have to prove is that this limit here exists. Okay, this is the claim. Okay, this is what we have to prove. Okay, now you see that. Obviously this integral is larger or equal than this integral. Sorry, this is a claim. Sorry. So obviously this integral is larger or equal than this integral. Okay. Now, and everything is larger or equal than 0. Okay. But this doesn't matter. This is not important anyway. So I should write here dx. Now, what we know is that if t tends to infinity, we know that this limit here exists, okay? But of course, from this, we cannot conclude that this limit exists, okay? Because this is just a sequence which is, we know if this limit exists here as well, okay? Then, and we take the limit here, then this, if you replace t by infinity, will be larger or equal than this if you replace t by infinity. But what we have to prove is we know that if t tends to infinity, we know that this limit here would exist, okay? But how do we prove that this limit also exists as t tends to infinity? Existence, how do we prove it? Okay, so you see this looks trivial, but not so easy to prove. Okay, we are essentially lacking something. Okay, so the main thing is, okay, how do you use this here in order to conclude that if as t tends to infinity, this limit exists, that this limit exists as well? How do you conclude this? This is actually more complicated than it looks like. Okay, so just to make you aware that this seems to be trivial, but it's not so easy to prove. Actually, as I said, you're just lacking one tool, and this tool is a so-called axiom. So this is something that the thing we are lacking is something which you have to prove, which you do not have to prove anyway. Okay, but this we are lacking here. It looks quite innocent, but in order to prove this, the question goes back to goes all back to a question we have never clarified, namely how to define the real numbers. But you cannot see any relationship. Okay, but we accept these results. Actually, we will prove something similar next semester for series, and then I will introduce the tool which we are lacking here. So next semester, I will come back to this point. Now, but this result is helpful in order to figure out whether a given improper integral is convergent or not. Okay. Because you can use this, in the convergence case we saw already, you can use this to prove that the given integral is convergent. You also get a bound for the value, okay, as we have seen from the proof here. Because if you know that if you have two sequences, if f of x is smaller or equal than g of x, and if x tends to a, the limit of f of x as x tends to a exists, and the limit of g of x as x tends to a exists, then the limits must also preserve this inequality. Okay, so what you get also, if you can prove convergence by this here, you will also get a bound for the value, but you still do not have the value. I just show you one example which is an important one, namely this one. Okay, so this is type 2. We want to prove that the integral is convergent. Now you see that the first thing is you can obviously break this into two parts. Let's go from to 1, and then plus 1 to infinity. Okay, and this part here will exist, no problem. So we have to check this part here. Now for this part, okay, so our function g of x is equal to e to the minus x squared. And for our function f of x, that's the reason why I write it like this. You can choose x times e to the minus x squared. Okay, so you will see that indeed you have g of x is smaller or equal than f of x for all x larger or equal than 1. We also saw already that the integral from 1 to infinity x e to the minus x squared, okay, we saw already that this integral exists. This is 1/2. Okay, so in particular exists. So now you can use the comparison test, and from the comparison test you will get that this integral exists as well. I should say convergent. Is convergent. And moreover, we get that the value is smaller or equal than 1/2. Okay. So for this example, this is important because the reason being you cannot if you write this as the limit t tends to infinity integral from 0 to t e to the minus x squared dx. Okay. You cannot evaluate this. Okay. Because in order to evaluate this, you need the antiderivative of this function here. And as I told you already several times, it can be proved. With the functions you know, you cannot find the antiderivative. It's not possible to express the antiderivative in all the functions we know. So this is not possible. In order to determine whether this improper integral is convergent or not, it's not possible to directly go to the definition. We need this kind of comparison test. Okay. So we know that this integral is convergent. The next question would be, okay, what is the value? Now you see, here you already see that the value is smaller or equal than 1/2. Okay, but this and larger or equal than 0, so it must be between 0 and 1/2. Okay. I tell you, it's not so easy because the value is this one. Okay, square root of this is not possible. Where is the because we have also this part here. I didn't. This integral is not smaller or equal than 1/2. I said it wrong. This integral is between 0 and 1/2. You have this as well here, which you have to add. So for this integral, you have square root of pi/2. Okay. Now we will prove this very easily next semester. Okay. You need if you have more tools, it's more easy to prove. It would be actually possible to prove at this stage, but in order to prove something like this, the only possibility you have at the moment is you're using here the Riemann sums. Okay, so you write this as a limit over the Riemann sums, and you try to find the limit like this. Okay, it's possible but complicated. You see it already from the answer. And this is something which is important in probability theory to know this. Okay, so any questions to this? So you see, this is a good example for an improper integral where it's easy to figure out whether that the integral is convergent, but complicated to find the value. Okay, and there are quite a lot of examples which run along similar lines. I'll show you another interesting example. Of course, you can also combine improper integrals of type 1 and type 2. Okay, so sometimes the integral is also improper, but it's neither type 1 nor type 2 because it's both. Okay, so for instance, look at this function here. Look at this function here. Okay, so where alpha is any real number. Okay, you choose a real number for alpha, and you consider this improper integral. Okay, so the question is, which alpha does this integral exist? Okay, now if we or is convergent. Okay, so you see that for instance, if alpha is smaller than 0, okay, because if t gets close to 0, okay, this will be close to 1. Okay, so you can look at it as 1. Okay, if t is sufficiently close to 0, this will be like 1. Okay, now if alpha is smaller than 0, you see that you have a point here. You have a type 2 improper integral. Okay, if and because of infinity, you have a type 1 improper integral. Okay, so this can be both, unless alpha is of course if alpha is larger or equal than 1, there is no problem. But if alpha is smaller than 1, okay, you have both type improper integral of type 2 at 0 and the improper integral at type 1 because of infinity. Okay, so the question is, for which alpha does this integral converge? Now, roughly speaking, because of this e to the minus t, okay, if t tends to infinity, okay, because we know that e to the minus t tends to infinity, tends to 0 more quicker than all functions 1 over t to the b. Okay, so because of this behavior, okay, for infinity there shouldn't be any problem for all alpha, but there is certainly a problem at 0. Okay, because for 0, if t is close to 0, you can say this is equal to, you can look at this as 1. So we know we have t to the alpha minus 1, and this is convergent if and only if this alpha is larger than 0, as we have seen before. Okay, but to make this precise, you need a comparison test. So normally, if you have such a problem, the first step is to get a feeling, okay, for which alpha should the integral exist. Okay, so in order to really make this precise, what I said, okay, you are going again to divide the integral into 2. Plus the integral from 1 to infinity, t to the alpha minus 1, e to the minus t dt. Okay, now if we assume that alpha is larger than 0, okay, so if we look at the first integral, you have actually, because I showed you the comparison test, I just showed you the comparison test for type 1 improper integrals, but for type 2 you have the same test. Okay, so you see that in this situation, because you can estimate this integral by the integral from 0 to 1. Now e to the minus t will be smaller or equal than 1, so you have t to the alpha minus 1 dt. Okay, and we proved before that for alpha is larger than 1, this integral is convergent. Okay, or in other words, this function is smaller or equal than this function, and the integral over this function is convergent. Everything is larger or equal than 0. This means because of the comparison test, now for type 2 integrals, this integral is convergent if alpha is larger than 0. Okay. So this is for this part here. So we know this part is convergent. Okay. Now we still have to handle this part here. Now for this part, so we have still to handle this one. For this part, it's actually we know that if t is large enough, okay, then this function will be smaller or equal than 1 over t to the b, or let's say t no, it's not a good choice. Let's say a good choice would be 1 minus alpha. Wait a moment. Oh, alpha plus 1. This is a good choice. Because alpha is larger than 0, okay? So this here, 1 over t plus alpha plus 1, okay, tends to 0 as t tends to infinity, okay? Now, we know that this function tends quicker to 0 as t tends to infinity than any of those functions. Okay, so if you fix this exponent, you will have for some t which is large enough. Okay, so let's say larger or equal than a, you will have that this is satisfied. Okay, so if we look at this integral here, you see that this integral will be smaller or equal than the integral from a to infinity. Now you plug this in here, and you get dt over t squared. Okay, and this here is convergent. Okay, so you see that this is convergent as well. So this implies that this integral is convergent. Okay, so if you split this integral into one from 1 to a and then from a to infinity, you get 1 to a is of course exists, and from a to infinity exists as well. So overall, we have shown that for alpha is larger than 0, this integral is convergent. Okay, so you see this is kind of to work out those details is kind of you have to spend a little bit time. But the important thing is you should understand that if you just roughly consider this integral, okay, as t tends to infinity, this function should still, because of course you have this factor, okay, but this function should still tend to 0 very, very quickly, okay, because of the e to the minus t. This is just expressed by this fact here. Okay, so as t tends to infinity, this function should go to 0 very, very quickly. So infinity should not cause a problem for every alpha. Now, if t tends to 0, okay, you can say if t tends to 0, this function will be roughly 1. So what you have is t to the alpha minus 1. Okay, but we have seen that such functions are convergent if and only if alpha is larger than 0. Actually, if you consider the case alpha is smaller or equal than 0, you can prove that this function indeed does not, this integral indeed does not exist. Okay. The reason why I mentioned this is because this function also important in application. So if alpha is, we just showed if alpha is larger than 0, then this integral is convergent from 0. So if alpha is larger than 0, this integral is convergent, okay, and will define you a new function which depends on alpha. And this function is normally denoted by gamma. This is called the gamma function. Okay, so for all alpha larger than 0, the gamma function is defined by this integral. Okay. Now you might wonder why this definition. Okay, actually this function is very important. Okay, so this is one function which you will encounter frequently in all kinds of applications. Now you might wonder, okay, why is this function important? Okay, so let's check out what is the function value of this function for at n plus 1, where n is an integer. Okay, so in this case, you have the integral from 0 to infinity, t to the n, e to the minus t dt. So n is an integer now. Okay, so we plug in for alpha n plus 1. Okay, and we want to interested what is the value of this function, of the gamma function at n plus 1. Now you see. Because this is an integer here, so what you're going to use here is integration by parts. So you differentiate this one, and you integrate this function. Okay, so you have t to the n, then integrate this function, so minus e to the minus t, evaluated at 0 and infinity. And then you have minus minus, so the derivative of this one, so the integral from 0 to infinity, the derivative of this one, which is a n, t to the n minus 1, and the integral of this one, which gives you minus e to the minus t. Okay. So you see that if you look at this part here, okay, as t tends to infinity, okay, because this function will still tend to 0, okay, because e to the minus t tends to 0 faster than any power. Okay, so as t tends to infinity, the upper limit, this will be 0. As if you have a natural number at the lower limit, this will be 0 as well. So this part will completely disappear. So you have n times the integral from 0 to infinity, t to the n minus 1, e to the minus t dt. Okay. Now you see that you have a recursion formula now, because this here, what you have here is just gamma n. Okay. Now what you do is you iterate this. If you iterate this, you will end up with n factorial gamma 1. Okay, but gamma 1, if you plug in gamma 0, no, gamma 0 is not defined, so this gamma 1. Now, but if you look at the case n is equal to 1, today we computed it, okay, so this case gives 1, so what you get is n factorial. Okay, so this means that gamma n plus 1 is equal to n factorial. Okay, and this is the reason why the gamma function is defined. Okay, because if you have n factorial, you know the definition of n factorial is n times n minus 1 times and so on times 1. So there is often the question, okay, is it possible to define this factorial, okay, in a way which makes sense if n is not an integer but a real number? So is it possible to define somehow this here? Okay, where x is a real number. Obviously, you cannot use this definition here, okay, if x is a real number. For instance, the question is, okay, is it possible to define this here? Okay, and this is a way to define it. That's why the gamma function is important, because it's a natural extension of this symbol here to all real numbers. Okay. So you will encounter this function quite frequently, the gamma function. That's why I introduced it by improper integral. Because I just want to spend the final time, just a few minutes, to tell you something which is interesting, but which I'm not going to prove. You will hear this later in other courses, just that you are already kind of familiar with this. We normally define also another function like this. Normally we define also a function like this, which is called a beta function. So this is the beta function. Okay, if so this is called the beta function. Again, you need that alpha and beta both larger than 0. Okay, so if you have two variables, alpha and beta both larger than 0, we define a function like this here. Okay, both functions are important in probability theory. Okay, you will recognize this today in the in-class homework. Okay, the example was this function here, where alpha is a plus 1 and beta is b plus 1. Okay, now Euler proved the interesting identity. The beta function and the gamma function are connected. Namely, you have this here. Okay, if you know this, then today's in-class homework is trivial, because you have the integral from 0 to 1, t to the a, 1 minus t to the b, dt. So this is beta of alpha plus 1, beta plus 1. So you have here alpha plus 1, beta plus 1. So you have here gamma of a plus 1, gamma of b plus 1 over gamma of a plus b plus 2. But I just showed that gamma of a plus 1 is a factorial, gamma of b plus 1 is b factorial, and gamma of a plus b plus 2 is a plus b plus 1 factorial. Okay, this is the answer. Okay, so if you know this here, but of course you are not supposed to know this, but if you know this here, the exercise is trivial, one line, finished. That's why I chose this example. Okay, so this is just to tell you that in mathematics there are many more functions which you haven't learned yet, like gamma, beta, and so on, much more functions. But you will encounter them afterwards frequently in applications because, as I said, both functions are, for instance, important in probability theory. Okay, so any questions?